We succeeded in the last lecture in determining the age of the asteroids to high precision. But where did they fit into the story? And what preceded their formation? Some relatively short-lived radioactive isotopes tell us much about the solar system's early days, provide a hint of what might have made it come into being, and may even solve the mystery of why all life's amino acids are left-handed. In particular, traces of extinct radioisotopes, long vanished through decay, provide clues as to how long it took for solid material to condense out of the protosolar nebula. Solar systems form as a spinning cloud of interstellar dust and gas collapses to a central sphere, which makes the star, plus a thin disk of orbiting material left over from that collapse, which form the planets. We see this process at work today in regions where stars are forming now in our galaxy. This series of spectacular pictures from the Hubble Space Telescope reveal what's going on. Now I must emphasize, these are pictures of the sky. They're what it actually looks like up there. They're real visible light pictures. The colors are real. The pictures are formed by taking images in several different filters with different colored filters over the lens of the camera, if you will, and then piecing them together in the computer. But they do represent what space actually looks like, where clouds of gas are coming together to form stars. Several things are prominent in all of these features. There is light and there are dark regions. The dark regions are not an absence of stars or an absence of light. The dark regions are where the dust grains, little tiny particles of dust, sooty kind of material that I spoke about earlier, come together in such profusion that they block the light from the background. You can see that clearly in these pictures. They're often in long strings and filaments and turbulent areas. Recall that this gas began as gas spread throughout space at 1,000,000 degrees and gradually cooled off. When this gas falls together under its mutual gravitational attraction, it's not surprising that it's a little turbulent and disordered. We often see in these pictures very thin filaments of this dark, dusty material. Those are the solar systems in formation. The pillars of dark gas that we see often may contain dozens or even hundreds of stars because they weigh thousands of solar masses each in molecular gas and cold dust. But as individual regions start to collapse, because of the random turbulent motion, this piece over here might be rotating in this direction. As something that rotating collapses, it spins faster. You're all familiar with the figure skater. She flings out her arms at the end of her routine and then goes into the death spiral, not because it looks pretty, but because as you draw your arms in, as you shrink your radius, you spin faster. That's exactly what's happening in these interstellar clouds. As the material falls under gravity towards the big mass in the center, it's rotating in some random direction. That spin just gets faster and faster and faster. And so while the central object, because of its large gravity, becomes a sphere, the material left over becomes a thin disk, a very thin disk that stretches out from that sphere to billions of miles. When we peer deeper into these regions of star formation, we can actually see these disks being formed. These are pictures from the Orion Nebula, the nearest region of massive star formation going on today, about 1,500 light years, or about 6,000 trillion miles from Earth. We see here 4 examples of what we believe are solar systems in formation. In the center of each is a little bright spot, brighter in some, dimmer in the others, always quite red. Why is it red? Well, for the same reason that the sun is red as it sets in the west. As the light from the sun passes through greater and greater amount of atmosphere, the rays are scattered away, and so rather than coming directly to you, illuminate the whole sky. The scattered rays are most effectively deflected if they're short wavelengths or blue light, which is why the sky is blue most of the time. But as the atmospheric path gets longer and longer, as the amount of dust and air molecules the light must pass through gets greater and greater, longer and longer wavelengths get scattered as well. First the green, then the yellow, then the orange, until the only thing coming directly at you from the sun is red. Well, that's exactly what's going on here. The light from that central star is surrounded by this dusty disk, and as the light comes out towards you, it's scattered through more material, so the blue light goes off in other directions, and the green light and the yellow light, and only the red light gets through. The disk itself is dark, black, again, not because there's nothing there, but because there is something there blocking the light from behind. All these little dust particles are packed so densely together that they're blocking all the light from behind. They are glowing themselves, but not in the part of the spectrum our eyes can see. Recall that our eyes are carefully tuned to the part of the spectrum the sun puts out with a temperature of 5,000 degrees. These dust particles are much colder, maybe a few hundred degrees above absolute zero, and so while they're radiating energy, it's in the infrared part of the spectrum that our eyes cannot detect. This was the circumstantial evidence that we had until recently that other stars may contain planets. But as I mentioned last time, we now have much more direct evidence that solar systems are common. Indeed, many young stars, after they're formed, are seen to still have this thin disk of material around them. Here are two examples, one seen face-on, that's rotating this way, one seen edge-on, that's rotating this way, of two stars where the central star has been blocked out by a little mask put in front of the telescope called a coronagraph, and all you see left is light from the star that scattered off the dust particles in the disk. In both instances, you see the size of Neptune's orbit, the most distant planet from the Sun, drawn to scale in the figure. And you can see these dust disks are a couple times the size of Neptune's orbit, just the size to make new solar systems. Very recently, at the end of 2008, the Hubble Space Telescope took what is the first actual picture of a planet around another star. The star is Fomalhaut, one of the bright stars you can see with the naked eye in the sky, and like many young stars, it's surrounded by a disk of dust. In this case, again, the coronagraph has blotted out the light from the star so you can see the light from the disk. And the astronomers involved in this project took these very deep pictures with the Hubble Space Telescope. And on the left, you see a tiny little dot inside the circle that comes from the square in the upper right-hand part of the picture, which might be a background star, might be a slight enhancement of the dust, hard to tell what it is. But when they came back and took the same picture 2 years later, as you can see in the right-hand picture, the little spot has moved. And indeed, since we can calculate the distance from the parent star, and we know the mass of the parent star, we know exactly how far it should have moved in that 2-year period. In other words, how long its year would be if it orbited around the star. And indeed, it moved precisely the right amount in precisely the right direction. This is a planet orbiting another nearby star. A young star whose dust disk is still mostly there and is probably still in the process of forming planets, as our solar system formed 4 billion years ago. Different materials condense out of this nebula of gas and dust and become solids at different temperatures, and thus at different distances from the parent star. As the star contracts and starts to shine, by processes we'll describe next time, it starts to illuminate this disk and warm it up. But clearly the closer you are to the star, the warmer it's going to be, and the farther away you are, the colder it's going to be. What we'd like to know is when exactly, in each of these regions of the disk, the dust particles could stick together, first to form little microscopic particles, then to form macroscopic particles, then marbles, then rocks, then boulders, then asteroids, and ultimately come together, coalescing under their mutual gravity to form planets. We know the basic physics of how this condensation process occurs for different kinds of elements, but to calculate from first principles exactly when this occurred in detail is essentially not possible. We use, therefore, the radioactive isotope plutonium-244 to provide a direct measure of the time it took this process to proceed. Now, those of you paying close attention might be a little surprised that I'm using the element plutonium because it's number 94 in the periodic table. And you're always told, and indeed I have even said, that the naturally occurring elements run from 1 to 92. That's a slight misstatement. Indeed, all the elements in the current periodic table, which run up well past 100, are naturally occurring in that they can be produced in natural processes, which we'll describe in the next couple of lectures. But all of the heavy ones are radioactive. They're produced in tiny amounts, and they decay away. So very few of them are found. Plutonium-244, however, is produced in stars at the end of their lives and has a half-life of 83 million years, which is short compared to the age of the solar system, but not zero. This is the most stable form of plutonium. The kind that we use in nuclear reactors today, plutonium-238, has a much shorter half-life of only 88 years. It's used both in nuclear reactors on the ground and to power spacecraft that travel far from the sun. Spacecraft that orbit the Earth, of course, gain their energy from solar panels, from panels that convert sunlight into electricity. And the Earth is close enough to the sun that a moderate-sized panel covering the spacecraft can provide all the power that it needs. But if one wishes to explore the outer solar system, as we have with satellites over the past 30 years, one gets farther and farther from the sun, and as a consequence, the amount of solar energy gets weaker and weaker, making the solar panel requirements larger and larger to provide enough electricity to the spacecraft. For very large and complicated spacecraft, which want to send back lots of data in the form of beautiful images and atmospheric measurements, like the spacecraft Cassini, which is currently exploring the Saturnian system and had its little capsule parachute onto the moon of Saturn, Titan, it requires so much energy and is now so far from the sun that a nuclear reactor was required. So a very small amount of plutonium-238 was included in the reactor on that spacecraft to give it power. Since the half-life is 88 years, that spacecraft can be powered for a very long time by this small amount of plutonium. But it's not the plutonium-238, the kind we make and use in reactors, but plutonium-244 that gives us a clue about the early solar system. It decays through 3 alpha decays to thorium-232. Now, thorium-232 occasionally decays itself through a very rare process of spontaneous fission. We've yet to talk about this kind of nuclear transformation. So far, we've focused only on radioactive decay, which involves the spitting out of an electron or a positron, an alpha particle, 4 particles of the nucleus, or a gamma ray. But there's another kind of nuclear reaction that can occur when a nucleus is so unstable that rather than just spitting off 1 or 2 particles to reach a more stable state, it actually splits roughly in half into 2 nuclei, which weigh half as much as the original one. This process is sufficiently violent that it spits out lots of extra neutrons as well. Sometimes 3, 4, 5, 6, 7 neutrons go off independently from the 2 chunks of matter that are left behind. The half-life for this spontaneous fission in thorium-232 is 13.9 billion years, almost precisely the age of the universe, meaning there's still lots of it around. This violent splitting of the nucleus produces 2 important effects. Since hundreds of millions of electron volts are involved, remember the light our eyes see is about 1 electron volt and results from atoms having electrons jump between energy levels, the nucleus is much more energetic because it's much more tightly packed, and its processes typically involve millions of electron volts. When you involve hundreds of nuclei all participating in some process, you get hundreds of millions of electron volts given off. And this event leaves a microscopic track in the meteoritic material from the atom, the 2 halves of which go rocketing off at close to the speed of light. They smash apart the crystal, leaving fractures on a microscopic level that, in principle, one could measure and learn about the process and when it occurred. This fission track technique is used in dating rocks on the surface of the Earth all the time, and even sometimes in dating fossils. However, for things as old as meteorites, these tracks gradually heal themselves as the displaced atoms find their way back to where they belonged in the crystal lattice, and so they've faded out almost completely by this time in the solar system's history. However, the expelled neutrons, often several neutrons coming from each fission, combine with other nuclei to make exotic isotopes, and it's these we can use to understand the original condensation of the solar system. In particular, both iodine-128 and iodine-129, very rare isotopes of iodine, are produced by neutron capture, the neutron combining with the dominant stable isotope of iodine, 127. Both heavy isotopes of iodine decay via beta decay to the corresponding isotopes of xenon, 1 step up in the periodic table, xenon-128 and xenon-129. Now, as a noble gas, xenon never combines with anything to make compounds, and should not be present at all in condensed rocky material, which was initially molten and therefore from which gas would easily escape. When examining the meteorites, however, one finds both xenon-129 and xenon-128 together with iodine-127, from which its now deceased parents were made. The ratio of xenon-129 to iodine-127, roughly 1 part in 10,000, provides a clock to measure how fast the material condensed. A high ratio implies early formation because all the xenon-129 that decayed was trapped and locked away as soon as the material condensed, whereas a low ratio implied that it took a while for the material to come together and trap the xenon. Most of the xenon had escaped. We collect meteorites that fall to Earth and examine their isotopic composition. There are several types of meteorites that are quite distinct from each other because of their distinct formation histories. Iron meteorites are made mostly of metals, and since iron is the most abundant of the metals, mostly of iron, and clearly were melted and then condensed into large globules. The largest of these meteorites we have are about the size of me. There are stony iron meteorites that consist of a mix of iron metals with composition of silicon and aluminum and other kinds of materials that condense into crystals or rock-like materials. These formed in a different location under different conditions. Finally, there are the stony meteorites that contain almost no metals at all, but just consist of rock-like material. Of this latter category, there are kinds that contain just pure rocks, and then there are kinds that contain things called chondrules, little tiny things from microscopic up to the size almost of a marble that are spherical globules of silicates, which are, by our models at least, the very first things to condense out of our solar nebula. Tiny little microscopic to ball-sized things that contain silicate material, silicon and oxygen, the first abundant elements that form together to make solids. The carbonaceous chondrites are yet a subcategory of these chondritic materials, which is a subclass that contains less than 5% of all meteorites, but includes a high degree of both water and organic compounds inside these little globules of silicate material. This implies, since the water is volatile and if it were hot would evaporate, and the organic materials are very delicate compounds, that these globules have never been heated after they were formed. They are, therefore, we conclude, the most primitive and earliest type of meteorite. They show, when we examine their xenon to iodine ratios, a very narrow spread in condensation times, all clustered around a value of about 12 million years. And so this is the period that it took for the early solar nebula to begin to condense into solid particles. This provides us with the first quantitative clue about the earliest events in the formation of the planets. Extinct radioisotopes also provide a clue as to what happened just before the solar system formed. Many iron meteorites show obvious signs of differentiation. You recall when I discussed the Earth that the light rocks, 2 to 3 grams per cubic centimeter, exist on the surface, and the heavy metals have all sunk to the core. When the Earth was molten, like oil and vinegar, the light ones rose to the top and the heavy ones sank to the bottom. In these meteorites, which are small, this kind of size, the same thing occurred. The heavy metals are on the inside and the light minerals are on the surface. This provides strong evidence that after they came together, after they solidified, long after the first 12 million years, when the chondrules were formed, something melted the asteroids. Now, on Earth, the heating that leads to the Earth being molten and the fluidity which allows these atoms of different mass to separate from each other is just a consequence of gravity. Things falling onto the Earth, like the asteroid that killed the dinosaurs, come in with tremendous speed and produce an enormous amount of heat just from converting gravitational energy to heat energy, the jiggling of atoms. But asteroids, even the ones a couple hundred kilometers across, let alone the ones that are the size that would fit in this room, have way too little gravitational energy to have melted the material. that can't be the explanation for how they differentiated with the heavy metals on the inside and the light material on the outside. An alternative is radioactive decay. This is also a heating source in that when a nucleus undergoes a transformation, it spits out a very high energy particle, typically with energies of millions of electron volts. That particle runs along, rattling off atoms in the material in which it was formed, and as it bounces off, it transfers some of its energy. What does that mean? It means those molecules that it hit jiggle faster. What does that mean? That means it's hotter. Indeed, if enough energy is released, it's so hot that the rigid bonds holding a solid in place are broken and it becomes a liquid. In a liquid, the heavy molecules can sink to the center and the light molecules can rise to the surface. Now, if radioactive decay is to be the explanation for differentiation in these asteroids, we need it to be an abundant species, and we need it to have the right kind of half-life to have decayed away over the early part of the solar system's history. Aluminum, it turns out, is one of the most abundant elements that are produced in stars outside of hydrogen and helium, making up over 2% of all the heavier elements. Aluminum-26 is a radioactive isotope which, when it's produced in the cores of stars, constitutes about 50 atoms out of every million aluminum atoms produced. Aluminum-27 is the stable one which completely dominates the amount of aluminum made. Aluminum-26, however, undergoes a beta decay with a half-life of only 730,000 years, releasing 4 million electron volts for every decay. Now, we can do a simple little calculation. Aluminum-26 is 50 out of every million atoms of aluminum, and aluminum is 2% of all the elements, again leaving aside hydrogen and helium, which don't participate in the formation of asteroids. Helium because it's a noble gas, hydrogen because it doesn't condense until very low temperatures. And so 2%, 0.02, times 50 atoms out of every million means that 1 out of every million atoms that condenses into a solid form will be aluminum-26. Now, it takes considerably less than 4 electron volts to break the bonds that holds the solid material in the asteroid in place. In other words, to melt that material so the solid, where the atoms are rigidly locked, turns into a liquid where they can flow over each other and the material can differentiate. 4 electron volts per atom, and yet we have 1 in a million atoms being aluminum, but each aluminum decay produces 4 million electron volts of energy. And so we have just enough energy in the aluminum-26 alone to melt the asteroids and explain their mysterious differentiation. But in fact, it's not just this indirect evidence of differentiated asteroids. There's more solid evidence that this short-lived radioactive isotope was indeed present at the birth of the solar system. Aluminum-26, aluminum being number 13 in the periodic table, undergoes a decay to magnesium-26, number 12 in the periodic table, by spitting off a positron and the inevitable neutrino. Now, it turns out 11% of all the magnesium on Earth is magnesium-26. But in the chondrules, what we do is use a technique similar to that I discussed last time of making a ratio from magnesium-26 to the stable isotope magnesium-24 and aluminum-27, the stable isotope of aluminum, to magnesium-24. Magnesium-26, remember, is the product of the aluminum-26 decay. It turns out there's a beautiful correlation between the amount of magnesium-26 in excess of what one would expect with the amount of aluminum-27 that's present in these chondrules, confirming that magnesium-26 is indeed from the decay of the sister isotope aluminum-26. Where there is more aluminum, there is more magnesium-26. Where there is less aluminum, there is less magnesium-26, just as we'd expect if the excess magnesium-26 all came from this decay. Now, the question arises, where did this short-lived radioactive isotope come from? It must have been produced within less than 10 half-lives or so, or less than 10 million years of the solar system's birth. Because after 10 half-lives, a half times a half times a half times a half times a half means that we're down to only 1/1000th of the original abundance. And that wouldn't be nearly enough to have melted the asteroids. So this radioactive isotope had to appear on the scene at the time the solar system came into being, right at the same time, not eons earlier, produced in some distant other star. The primary source of aluminum-26 is massive stars which explode at the end of their lives. As we'll learn in the next two lectures, stars are the factories which produce atoms. All of the atoms, besides hydrogen and helium, were cooked up inside stars. And this applies to the stable isotopes as well as to the radioactive ones like aluminum-26. In addition to creating things like aluminum-26, these massive stars end their lives with huge explosions, which disgorges all the atoms they've cooked up over their lifetime, but also leads to a blast wave that rockets through the interstellar medium, a sonic boom, if you will, crashing in to any clouds in the way, and, quite possibly, triggering those clouds to start to collapse. The pressure wave pushes matter together. Once there's an excess concentration of matter, gravity can take over and material can fall from all different directions, building it up to the size of a star. But this trigger of a stellar explosion might be essential to producing stars. Indeed, when we look in the Orion Nebula today, this nearby region of star formation, we see directly the remnants of exploded stars running into those clouds of material that have yet formed stars and compressing them in just such a way to trigger the collapse of star formation. Indeed, looking in distant galaxies, we can see the overall architecture of the galaxy is governed by the explosions of these stars. In addition to producing radioactive isotopes like aluminum-26, and in producing the shock wave that might have triggered the collapse of the solar system, such an explosion also often leave behind the collapsed core of the now dead star in the form of one of these bizarre objects called a neutron star. The core of the star collapses so rapidly that the electrons are driven into the nuclei of the atoms, combining with protons. An electron plus proton makes a neutron. The other neutrons are still there, and the entire body of the star is principally neutrons. The collapse, as I said earlier, leads anything that's spinning to spin faster, and so these objects spin very rapidly. And in addition, the collapse amplifies the magnetic field that would have been present in the star, leading to the extremely rapidly rotating, magnetized, incredibly dense object that could have illuminated the early solar system with the circularly polarized light that preferentially destroyed the right-handed amino acids, the molecules with right-hand symmetry, leaving an excess of left-handed molecules which came to yield life today on our planet. Reconstructing the origins of our geology and our biology at a distance of 4.56 billion years is a fascinating task. But the formation of the sun and the earth is far from the beginning. Indeed, over 2/3 of the life of the universe had already passed when this occurred. What came earlier? Indeed, a more fundamental question, where did the atoms in the pre-solar cloud come from? To answer that question, we must turn to examine the lives of the star, story that we'll undertake next time.